the next section, we'll consider another modeling scenario. So in this scenario, a spray adhesive is filled into aerosol cans on an automatic fill machine line in a plant. And every 4 hours, a worker takes a 55-gallon drum and hooks it up to the fill line by putting in a long 2-inch tube into the drum. And it takes the worker about 5 minutes to open the drum, slide the tube into the drum, and then make sure that the line is primed and there's no local exhaust ventilation. And the solvent of interest is hexane with an occupational exposure limit of 500 parts per million at about 25% of the total volume. And there is a limited amount of N-hexane, which is much more toxic, with an occupational exposure limit of 50 parts per million, and it's about 5% or less of the total hexane. The room dimensions are given as 20 by 40 by 12 feet, and the general ventilation is about 6 air changes per hour. And we also know the vapor pressure for N-hexane as 130 millimeters of mercury at 20 degrees Celsius. So we assume that there is a leak in the fill line, and as the adhesive mixture flows through it, there is a 0.01% loss to the room air over the 4-hour period. And so 0.01% loss corresponds to 55 gallons that you convert to liters. So you multiply by 3.78 liters per gallon, which you then convert to cc's. So that's 1,000 cc's per liter, and then the 0.01%. So that's 0.0001. So that comes out to be 20.8 cc's per 4 hours. And likewise, we can calculate a 0.1% loss. That's 10 times more, so it's 208 cc's per 4 hours. So we can use our well-mixed room model. So the volume of the room we can calculate as 272 cubic meters. The ventilation rate, also we can convert the 6 air changes per hour as 27.2 cubic meters per minute. And we can now calculate the mass rate of hexane as 55 gallons times 3.78 liters per gallon times 1,000 cc's per liter. And then we multiply it by the density of hexane, so 0.66 grams per cc. We convert the grams to milligrams, and we know that 25% of the volume is hexane, and there is the leak rate of 0.0001 over 240 minutes. So we get a mass rate of hexane as 14.3 milligrams per minute. If the leak rate were now increased to 0.001, we get 10 times the mass rate. So we would now get 143 milligrams per minute. And we can plot these two equations and predict the steady state concentration of hexane in the room. At the top of the slide, the threshold limit value TLV for hexane is given as 1,760 milligrams per cubic meter or 500 parts per million. And we see that for both of these assumed leak rates, the time-weighted average concentrations are either 0.5 or 5 milligrams per cubic meter. So they're both well below the TLV for hexane. So if we just go with this model, it does not matter what the leak rate is, and that we could be off by a factor of 10. It doesn't really make a whole lot of difference to our decision. So there's a tenfold difference in the actual concentration, but because both of the concentrations are so much lower than the threshold limit value, we are not really that worried about the effect of uncertainty in the knowledge about leak rate. Now let's do the same thing for N-hexane. The volume of the room and ventilation rates are the same as before. Now the mass rate of N-hexane, so the one thing we need to keep in mind is now the N-hexane is just 5%. And so we get a mass rate of 2.85 milligrams per minute in one case and 28.5 milligrams per minute in the other case for the different leak rates. And again, we plot the concentration versus time for N-hexane now. And the top of the slide, the TLV for N-hexane is given as 176 milligrams per cubic meter. But as these two plots show, even though the leak rate might be off by a factor of 10, the TWA concentrations are so much lower compared to the threshold limit value that we can easily say it does not matter that we don't know the leak rate exactly. And our decision about what to do in this case would not be that different. But now let's say that we are not so happy with the model itself. We feel like maybe the well mixed room model is not the best model to use in this scenario. We really should be using the near field far field model. So we go to this model. Again, the volume of the room and Q, they don't change from before. We can calculate the mass rate of N-hexane as before, so 28.5 milligrams per minute. We can calculate the volume of the near field as 2/3 times pi times 0.8 cubes, so about 1.1 cubic meters. And beta we can calculate again as 6 cubic meters per minute. And now when we plot the near field model, the concentration of the near field, if we assume a 0.1% leak, is only 5.7 milligrams per cubic meter. So it is still well below the 176 milligrams per cubic meter. So we say, okay, we don't really need to worry too much about it, even though we are now using a far more conservative model, and we have gone from 1 milligram per cubic meter when we assume the well mixed room model to 5.7 milligrams per cubic meter for the near field model. The bottom of this slide, you also see the far field model prediction, which is 1 milligram per cubic meter, which is the same prediction as the well mixed room model made previously. So, in summary, what this example showed is that even if we didn't know the leak rate very precisely, the concentrations predicted by the two models are very different, but it is still much, much lower compared to the threshold limit value. And therefore, it does not matter that we don't know what the leak rate is. And in fact, turns out it does not matter what model we use. But we can imagine situations where the near field, far field model would make a very different prediction compared to the well mixed room model. And it might lead to an entirely different decision about how to protect the workers.